The purpose of this video is to look a little bit about the environment around us within the extreme environments that we're studying in this unit. If you're going to provide any sort of clinical or medical care in an extreme environment, you're going to need to have some understanding of the pathophysiology of what's happening, and indeed the physiology and the physiological changes that can happen in that environment. And underpinning all of that actually is an understanding of the environment itself. If you don't actually understand what's happening around you, how can you possibly hope to predict physiology, pathophysiology, and clinical care? So in order to do that, we're going to step outside our normal field of study, outside of our health sciences. We're going to look at a few other sciences. We're going to start with a bit of geography. We're going to look at the Earth, the structure, the way the Earth operates, if you like. We're going to look a little bit at the atmosphere, a little bit about atmospheric physics that's relevant to us. We're going to touch on some meteorology and climate, a little bit on plate tectonics and mountain building, and finally on anthropology, human populations and how they've changed and how they've moved. First, we'll look at the Earth, and to do that, I've got the help of a globe. So we'll use this globe to have a little look at the Earth. When you purchase a globe from a shop, the Earth appears spherical. In reality it isn't, it's an oblate spheroid. In other words, it's flattened at the poles. We all know that the Earth spins about its axis, or actually wobbles slightly about its axis, as it orbits around the Sun. And we also know that the axis itself isn't straight up and down, that's inclined at an angle of about 23 degrees. That's actually quite important, and we'll see why now. If you can suspend disbelief for a while and accept that this is the Sun that isn't 93 million miles away from the Earth, we can look at how the Sun moves in relation to the Earth, and we can look at what happens at the poles. So here we have the Sun directly over the equator. It's the end of March, it's the equinox, there's equal light and equal darkness on every part of the globe. In spring, that Sun is going to appear to move north, and it's going to travel as far north as the Tropic of Cancer, 23.5 degrees north. And that line, that tropics of Cancer, and its equivalent in the southern hemisphere, the Tropic of Capricorn, those lines define the point at which the Sun it goes overhead, completely overhead. Any further north than that line, the Sun is never completely overhead. Any further south than the Tropic of Capricorn, the Sun's never completely overhead. So let's take our Sun back to the Tropic of Cancer and have a look at the polar areas. What we can see is that obviously this side of the Earth's being lit, but up here, the back side of the Earth's being lit as well. So whereas if we heard further south, down here, it's darkness, it's nighttime, even though it should be nighttime, Sun's rays are still striking this side of the globe up in the Arctic areas. And we can define the Arctic Circle as that point at which you get 24 hours of daylight and 24 hours of complete darkness. Because whilst the Sun's up here, we can see we're going to get some complete daylight. In contradistinction, as the Sun heads down south, we're now at the other end of the year, it's December the 21st, it's over the head of the Tropic of Capricorn. Even though this part of the Earth is facing the Sun, the tilt is such that we're not going to get any light there at all. And indeed, if we go more extreme and look at the poles, we actually see that there'll be complete darkness until the equinox, and after that, 6 months of complete daylight until the other equinox, and then 6 months of complete darkness. And so within the polar regions, we see that variation between a day of complete darkness, a day of complete light, through to 6 months complete darkness, 6 months complete light. That's actually really quite relevant to our study of human populations working in the Arctic and living in the Arctic, and working and living in the Antarctic. It has profound effects psychologically, physically, and on performance. We see a variation in cortisol and other hormonal levels. We see problems with sleeping and natural functioning due to those absence of normal day and night cues. And we'll have a look at those in a bit more detail as we dive into this unit. So that's a little bit about the Earth. Now let's look at what's encasing the Earth, and that's the atmosphere. And as we mentioned, the Earth's an oblate spheroid. It's flattened at the poles. That affects gravity and therefore affects the thickness of the atmosphere. At the poles, the atmosphere is about 7 kilometers up to the tropopause. The tropopause is that point below which the vast majority of the mass of the atmosphere is contained. So about 7 kilometers to contain all that mass. Out at the equator, we find that it's about 20 kilometers. The atmosphere is much, much thicker. If we think about the sun heating the Earth, it does so by radiation. The Earth absorbs that radiation and spits it back out again. And it will heat the atmosphere by conduction and a little bit by radiation, but predominantly by conduction. And therefore, the atmosphere closest to the Earth is going to be the warmest. Further away, the atmosphere is going to be cooler. We can conceptualize that as the environmental lapse rate. So that's the rate at which the atmosphere is cooling as we go up in the air. Whilst that rate varies, depends on a lot of factors, in particular humidity, we can give it a rough average as about 1 degree every 150 meters. So 1 degree of every 150 meter height gain is a reasonable figure to have in your head. We know from our chemistry and our physics that we probably did at school that the atmosphere contains nitrogen, about 78%, oxygen, about 21%, about 0.04% carbon dioxide, though in these days of global warming, really who knows how much carbon dioxide there is in the atmosphere, and also water vapor. Now, Dalton's law tells us about partial pressures, the sum of a partial pressure of an individual. Add them all together, you get the sum, you get the total partial pressure. That's fine. If we think also then about the mass of the atmosphere, close to the surface of the Earth, there's a lot of atmosphere pushing down. Further away, there's less. So pressure, barometric pressure, reduces as we go up. So we still have the same percentage components of gases in the atmosphere higher up. Just the overall partial pressure of each gas, the overall barometric pressure is much less. We can look at that in terms of physics and our ideal gas law, and look at pressure being inversely proportional to volume. As we go up, pressure decreases, volume increases. Admittedly, that relationship holds true for a given temperature, and in reality we are changing the temperature. But nevertheless, what we're seeing is a thinner atmosphere. Less oxygen. Hyperbaric hypoxia becomes very important when we look at altitude medicine. Let's also think about meteorology. So looking at climate and weather systems and what impact they have. First thing to talk about, of course, is the fact that when the Earth spins, it creates an apparent force known as the Coriolis force. It's the force that makes the water go down in the plug hole and spin as it does so. It's an apparent force, so the faster things are happening, the faster that force, the more strength that force has. And that's quite critical in changing the circulation of air in the atmosphere. From a meteorological perspective, we can look at the general circulation in the atmosphere. So coming back to our sun and where it is overhead, shifting between Tropic of Cancer, Tropic of Capricorn, we're certainly seeing that these areas of the Earth are getting heated much, much more than the poles. So we're getting gas rising, travelling outwards, affected by the Coriolis force, sinking and moving back in. We get these pressure cells developing. So as a rough rule, we can look around at the equator and say it's predominantly a low pressure area. High pressure areas, as masses are sinking, they tend to be dry. And funnily enough, we've got the this high pressure area exists exactly where most of the Earth's deserts are. So the Northern Hemisphere deserts, perhaps in America or in Asia, in Africa, are up around the 30-degree mark. Down this side of the world, down in Australia, again, look at our great desert areas are roughly around the 30-degree area. They're in areas that are predominantly high pressure areas. Again, looking at these circulations that we see, we tend to find that we've got low pressure areas in fairly high latitudes, around about latitudes of 50. And then again at the poles, what might seem paradoxical to you, again, these big high pressure areas of cold, dry air sinking. So looking at this general sort of circulation, we can then learn about meteorology at what's called a synoptic scale. So in other words, looking at perhaps the interplay around a continent of some cold fronts, warm fronts, high pressure areas, and then drill down even further and look at local scale. So what's actually happening around our coastline, for instance, in the summer, a sea breeze that might be happening. So understanding some meteorology at all three levels is quite important. Because that, combined with what we've been talking about so far, is going to tell us a little bit about the climate. We've already mentioned the desert areas. We can also think about the sea, which I haven't drawn in here to avoid complexity. The circulation, currents, ocean currents drive climate, proximity of land masses to the sea drive climate. So some understanding of all of these can help us to sort of predict what's happening around the globe. Where we are in Tasmania, the predominant westerly airflow that we get. Further south, around Casey Station in Antarctica, predominantly easterly flows. The southeast and northeast trade winds that characterize these tropical areas. So with that little baby introduction to meteorology, let's move back to our globe and let's look at sort of plate tectonics. Why are we looking at plate tectonics, you might ask? Well, it tends to give us an idea of where the high areas of the world are, the high altitude areas of the world. So we have a Pacific plate and the American plates meeting. We've got our high altitude areas down the west coast of America, down in the Andes, that's familiar to most people. The Himalayas, equally familiar to most people, where the Indian subcontinent's pushing up into the Eurasian plate. But we also have plenty of other much less well-known high-altitude areas. Kamchatka, Japan, Taiwan are on the edge of the plates. New Zealand, of course, Papua New Guinea, all on the edge of plates. If we think about us in Australia, we're actually nowhere near a plate. We don't really have any high-altitude areas, 2,200 metres being the highest point on mainland Australia. So a basic understanding of tectonics gives us an idea of where all our high altitude areas are going to be. And finally, I'd just like to consider a little bit about anthropology. Who's actually living in the areas where we're going to be working or playing? A good example might be in Tibet. We've got populations that have spread out across Eurasia, probably starting 1 million years ago. Certainly Tibetan people have been up on the high Tibetan plateau living at 4,500 meters for thousands of years. In contradistinction, China has tried to populate Tibet more recently with Han Chinese people. They're not adapted to high altitude areas, and they suffer medical problems differently from the Tibetans. Similarly, we can look at cold climates, perhaps up in the Arctic here, where again we've had populations that have been living there for several thousand years and are adapted to the cold climates. They function very differently, perhaps, from southern dwellers who are moving up there to work, perhaps on oil or gas pipelines. So in summary, if we can think about the shape of the Earth, how it moves, the relationships of daylight and darkness, if we can think about the atmosphere and some meteorology, we can begin to build pictures of what different parts of the Earth look like, we can begin to build some understanding of how our environment is going to affect our physiology.